Hello everyone, good evening. So today is going to be our last class. So today what we will do is we will not be solving any problems. We will just quickly revise what we did in this course so that it will help you when you go through your revision. It will help you for better understanding. So if you have any questions, what you could do is you can post in the common forum and before the exams I will be able to help you. uh, Looks like we do not have any audience today, so what I will do is I will quickly go through all the lecture materials that we came across in this lecture. Okay, so initially, how did we start is we just you know revisited our basics of thermodynamics. So here also what uh, I'm going to go through is I'm going to go through week by week basis in the same order how we learned. Okay, so in week one what we did was it's purely revisiting basics of thermodynamics. Since the course is advanced thermodynamics, um, we have to revisit some basic thermodynamics. That's why. So basically we learned some of the, I mean, it's not learned, we revisited some of the basic terminologies in thermodynamics like system, surroundings, universe and boundaries. And also we defined there are three kinds of system: closed system, open system and isolated system. In a closed system what happens, there will be energy transfer happening through the boundary, which means heat or work transfer can happen through the boundaries of the system, but mass transfer cannot happen. In open system, both energy and mass transfer can happen, and an isolated system, no energy and no mass transfer happens. That is basically the difference between these three systems. And any physical system can be modeled using either of these three systems, and we will be able to get good insights of it. So that is what we studied first, and then we also looked at thermal equilibrium. So what do we call thermal equilibrium? Basically zeroth law of thermodynamics we did, and then we also see what is we also looked at what is temperature, uh, and basically if system has to be in equilibrium, thermodynamic equilibrium, then it has to be in three kinds of equilibrium. All if only all three equilibrium are present, then only we call the system to be in thermodynamic equilibrium. So initially the mechanical equilibrium means there is no unbalanced force or torque. So system can be in either rest or in motion, that doesn't matter, but there shouldn't be any unbalanced force or torque. And for chemical equilibrium, in addition to the mechanical equilibrium, there should be no change in internal structure through reaction. So if there are reactions happening, then you cannot call it as a chemical equilibrium. So if there is no reactions happening, there is no chemical structure change or internal structure change, then we call it as chemical equilibrium. In addition, thermal equilibrium, when do we say thermal equilibrium is when we have no changes in the coordinates of the system, right? A diathermic wall. So which means we will allow heat to transfer to and from the system, which means we will allow heat to transfer uh, outside of the system, or we can take in some heat, but the coordinates of the system should not change with the diathermic wall. So if that is the case, then we will be in thermal equilibrium. So if all three equilibrium is satisfied, then we call it as a thermodynamic equilibrium. And what do we mean by coordinates of the state? So any system can be defined by two thermodynamic coordinates. It can be either PV or VT or PT, right? So with the two independent variables, you can define a thermodynamic coordinates, and the other one can be other variable can be we can find it by employing equation of state. So we have ideal gas equation of state, Van der Waals equation of state, and there are a lot of equations of state depending on its application, right? So uh, whether we are in high pressure, high temperature, low pressure, high temperature. So based on the thermodynamic variable, each gas behaves as a different behaves with a different equation of state. So that is the equation of state we did, and then we also define something called hydrostatic system. So in a hydrostatic system, we also define certain properties of this hydrostatic system. For example, volume expansivity, isothermal bulk modulus, isothermal compressibility. All these things, it's actually a relation between these thermodynamic variables P, V, and T. So this you can write this function. Basically, it's a mathematical function, and each term is going to correspond to these thermal volume expansivity, isothermal bulk modulus, and isothermal compressibility. So that is how we come up with these properties, and it all has physical significance, and then we also did some mathematical calculations, and then we end up getting, let's say, for a constant volume, how does let's say if the temperature changes, how does the pressure change, let's say, for example, if I want to know, then just by rearranging these equations you will be able to get it is going to depend on uh, you know the volume expansivity and the isothermal compressibility, right? So beta by k. So this is for a constant volume. Similar kind of things you can derive. And then important aspect is we also the studied about energy interaction. So energy can interact in only two ways. One is through work or heat. Right? This is how energy can get modified, and this paves us way to the first law of thermodynamics. So in energy interactions, we have work and heat as energy interactions for a system, and we also there is some convention. So if it's an heat is coming to the system, then it is positive. Heat leaving the system is negative. Work done by the system is positive. Work done on the system is negative. So that convention we will follow. And usually expansion process are work done by the system, and compression process is work done on the system. So you need to do some work in order to compress a material. So that is why it is called work done on the system. And basically we also know that PV diagram is called an indicator. So I just highlighted some important aspects which one should remember, uh, or which one should so upon going through this aspect, you will understand what are all the things we covered. Okay. So and then we also, for various process, how does this PV plot vary, so that also we studied. So basically there are different kinds of process like isobaric, isochoric, and isothermal. And isobaric means the pressure is constant, isochoric means volume is constant. So based on that, let's say if you want to express everything in PV power n equal to constant, then what would be the n? So that for different process you can find. So and and if that is the case, then what is the work done? Work done is going to be simply area under the PV curve. So let's say if it's isobaric process, this will be your work done. If it's a isochoric process, then you do not have any work done. There is something. And let's say if you have adiabatic process somewhere like this 1.4, then this is going to be your work done. So that is what this means. And based on that, we also derive some work done. It's basically PV work done by this closed system is nothing but integral of V1 to V2 into PdV. That is the work done. That's how we define work done. Everything is PdV, PV work. That is one of the assumptions we make. It is a simple compressible substance, so we have only PV as a work. Uh, and these are all the various processes. And if it's an adiabatic process, then we have something like this, uf minus ui. So if it's an adiabatic process, you are doing some work, which means no heat is going to come out, then something has to change within the system, and here the change is nothing but final internal energy minus initial internal energy. So whether you take any path, then since internal energies are state functions, not the path function, so this becomes constant for any path, given that initial and final states are true. All right. So And then we defined what is this internal energy function is. We call this a function because internal energy is going to depend on two independent variables. So either it will depend on T and V, or it will depend on T and P. So either of the two uh, independent variable it will depend on. So that's why it is called function. It is a function of temperature and pressure, or temperature and volume. And then we revised first law of thermodynamics. The first law of thermodynamics says the change in energy of the system is nothing but uh, you know the heat coming to the system. Heat is positive, so which is coming to the system, and work done by the system. Hello, Shiv. Are you able to hear me? I think Shiv is not able to hear me, or maybe his microphone is not working. All right. Shiv, if you have any doubts, you can ask me. So I'm just revising what we did in this course this today. I'm not solving any questions. So let me continue. If you have any questions, you can interrupt me. All right. So I hope I'm audible. Okay. So in first law of thermodynamics, what we did was we did that the first law of thermodynamics is nothing but the change in internal energy of a system is the internal energy of a system can change basically due to two things. One is heat input. Because of heat input, internal energy can change. The other is work done. So if the system does the work, then the internal energy can change. So that is why it is called. It is written simply like this: UF minus UI equal to Q minus W. Okay. And for an hydrostatic system, we will write something like this. For a composite system is nothing but let's say if you have one system and the second system, if there are just two systems, two hydrostatic system, uh, in between there is a piston or some wall, okay, which can move. So basically, then there are two kinds of PDV work you are doing. That's why we have different work, additional work terms. And going forward, we also define specific heat for constant volume process, specific heat for constant pressure process, which is nothing but amount of heat required for a small change in temperature. Basically, to generalize this, what people will do is the amount of energy required for a change in temperature of 1 Kelvin. If it is in a constant volume process, then it is called CV. If it's a constant pressure process, then it's called CP. So that is how we define CP and CV. And this is pure mathematics. So since you said that internal energy is a function of temperature and volume, uh, a small change in internal energy could be due to change in temperature and also could be due to change in volume. So it is coming from mathematics, partial differentials. So the total change in internal energy would be uh, will comprise these two terms, which means the partial change in U uh, for a small change in uh, temperature, keeping volume constant for a given change in temperature, and dou U by dou V at constant temperature times dV. So, and if we continue with this process, then we know that dou U by dou V at constant, since it's a constant volume, there's going to be there is no pressure work. So the change in internal energy is nothing but the amount of heat required, right, from first law of thermodynamics. So if you put that, then you get CV, and then you continue manipulating these equations, and then finally you will end up how does a change in internal energy with respect to volume works. So basically you will come up with this kind of, so these kind of equations basically comes from this equation and the knowledge of first law of thermodynamics. So if you know these two, you don't need to remember these. If you just know these two, you can always come up with such kind of expressions. Okay. And of course we need to do some practice in order to uh, in order to understand these concepts. So and then important thing, then heat pumps, heat engines, heat pumps and refrigerators we revised. So heat engine is nothing but it takes heat from hot reservoir and gives rejects heat to a cold reservoir, and while during this process it produces work. So that is what heat engine is. Heat pump does the opposite, but by taking the uh, you know uh, work as a input. Okay, so in refrigerator and heat pump are almost same, but the thing is, in refrigerator we are interested in removing heat from a cold space. In heat pump we are interested in dumping heat into the hot reservoir. So that is where that but both, basically both are same if you look at it in a physical perspective. Only thing is the area of interest is different from refrigerator and heat pump, and because of that we have coefficient of performance formulas to be little bit different. Coefficient of performance is nothing but desired output by work input, right? So that is the reason you will have a kind of different coefficient of performance, and it can be related like this. And uh, heat engine also has its efficiency. uh, Basically, let's say I have amount of heat, uh, what do you call, so basically you will see, you are interested in producing this much amount of work, but the amount of heat would be high, right? So let's say if you do that, then you will get the efficiency. And this
Sir,
yes,
sir,
yes, yes, yes.
sir, I have one problem in this equation.
Okay.
Sir, here it is written in the form of heat. How can we write in the form of temperature? That QH, in the place of QH, we are writing TH and TL. So, in which condition we can write heat in the form of temperature?
Right. So basically, if it is a reversible engine, okay,
Huh.
then you can replace Q to be T. That is the catch. If it's an reversible engine, that is when you will get highest coefficient of performance. Or let's say if you talk in terms of heat engine, that is when you will get, let's say if you use a Carnot cycle, right? In Carnot cycle, if you use, that is the highest efficiency you will get, because Carnot cycle is a reversible reversible cycle, and that is going to give you the highest efficiency. And that reversible engine, you can replace this QL and QH in terms of TL and TH, only if it is a reversible engine.
So, I can we can write QH equal to MCP dt या MC dt, and this one is your मतलब TR, thermal energy reservoir at higher temperature, that is TH. And in Q, we know Q equal to MC dt. So in this way, in reversible engine only possible, so can we write in term of temperature.
Okay, so basically, it is actually not coming from there. So
Okay.
it is due to the since it's a reversible process. Let me show you. If it's a reversible process, what happens is you can the entropy change would be zero. Okay,
Okay, sir. Hmm.
so I think I didn't write it here. So give me a minute. And that is the reason you can replace Q with T. It is not due to MCP delta T. So
Okay, okay, sir.
let me show you in the lecture notes. G, I think it's so.
Yes.
Which week is this? I think this one. Let's see. When we write in terms of so in a Carnot cycle, what happens here?
Yes.
We here we still write efficiency in terms of QL and QH, right? So
Yes.
this is a
G.
this is a function of TH and TL. That is what we know. But
Yes, sir.
since it's an Carnot engine operating between three reservoirs, okay, 1 second. This is
Hmm.
quite little bit complicated. Give me a minute. There should be an easier way. Okay. So what you have is you have three you know
Temperature. Three
three,
reservoirs.
I mean three heat engines, okay, two reservoirs,
Yes, sir.
but three heat engines, and there is one more
G.
reservoir, they, as you said, there is one more reservoir they have given here. Okay, let me do something. Instead of it, okay. So here what they
Yes,
have is
sir.
they have this high temperature, and there are this low temperature reservoir, and there is this heat engine, okay, working, so which takes heat from high temperature and give it to low temperature, and it generates
Yes, sir.
some work output. Now let's say
Work heat.
this is a reversible heat engine. Now let's say you introduce
Yes.
another reservoir, and you have two heat
Hmm.
engines where each engine is also reversible. This RB and RC is also reversible, and it takes Q
G.
from one side and give it to this
Temperature.
T3, okay, and then from here if you take Q3 and then give
Hmm.
it to Q2, so whatever Q comes is stored in this reservoir and the same Q is given here, okay. Basically you are dividing it into two, this you are dividing into two, and now you have two kinds of work coming out, okay. So now if you find the efficiency, then this QL by QH is so QL and QH is a function of temperature, some function, 5 is the function, this is some function of temperature. So QL by QH is also a function of temperature, right? So
Yes,
and
sir.
uh, and so the Carnot engine is operating between three reservoirs, the engine A has Q1 by Q2, right? Efficiency of engine A will be 1 minus Q1 by Q2.
Yes, sir.
It should be Q2 by Q1, right? Because QL by
Q2 by Q2.
Q2 by Q1. So efficiency of heat engine A is 1 minus Q2 by Q1.
Yes,
Then,
sir.
which means it is a function of some T1 and T2. We still don't know whether Q2 you can replace with 1 or T or not. Okay. Similarly, you can write this as a function of you know uh, T for engine B and C. Now, let's say if you, since arbitrarily chosen T3 should vanish, because you what you did was you divided into two. These two should vanish because reversible engines will always give you the same output. That is what the basically the law says, right? Second law of thermodynamics. Reversible engine is going to give me the highest efficiency, and how much hour you have lot of engines, let's say, okay, you have more than 2 3 engines in between the same reservoir, you still should get the same efficiency. That is what it means, right? So then
Yes, sir.
this, it shouldn't depend on T3, right? So that is why, let's say if you write it like this, then let's say function of 1 and 2 is nothing but, okay, so let me write it down for you. So engine A is 1 minus Q2 by Q1,
Yes, sir.
right? Which is Q2 by Q1 is a some function of temperature T1 and T2. Okay.
Yes, sir.
Similarly, if EB is nothing but it is Q3 by Q1, then
Q.
Q3 by Q1 is some function of T3 and T1, right? And efficiency of C is 1 minus Q uh, 2 by Q3. You see, 2 is the lower, right? 2 is lower and 3 is higher. So for the last heat engine, so then you can write Q2 Q3 is some function of T2 and T3. Okay.
Yes, sir.
Now what we are telling is these three. So let's say if I want to write this Q2 by Q3, you can write it like Q2 by Q1, you can write it like Q3 by Q1 times Q2 by Q3, right?
Okay.
Multiplication of these two can be written like this,
Yes.
right? So then what we know about Q3 by
Expansion
Q1
of
is
T3, T1.
T3 and T1. Similarly,
T1.
what we know
Yes,
is
sir.
this has to be T2 by T3,
2.
T2 and T3, right? These two
Okay.
should be function. So how did they write? So they write Q1 by Q2. Okay, we wrote in Q2 by Q1. Anyway, so um, so okay, let's follow theirs. Let's say if you want to write Q1 by Q2, then you will write this as
I
Q2 by.
understood, sir.
Okay, so you understood. That's good. So then you can write this as they wrote f of T1 by T3 divided by f of T3 and T2, right? This is what they wrote here.
So,
So this should be function of just T1 and T2, right? So
T3 is common in between.
so basically T3 can be anything. Let's say T1 is 500 and T2 is 200. So T3 can be either
So,
300, 350, 400, or even 250. Okay, it can be anything in between. This choice shouldn't affect your performance. Like for example, efficiency. This choice shouldn't affect your efficiency. The reason is all are reversible engines, right? Reversible engines are going to give you the same uh, efficiency. So
entropy condition is zero, sir.
right. For example, yeah, that's why. So this should be simply a function of T1 and T3. So which means these two things should vanish, right?
Yes, sir.
Then what happens? Q1 by Q2 is simply a function of T1 by T2.
T2.
So it can be any function of T1 and T2. And what we are taking is, we are taking it to be simply T1 and T2.
Okay, sir. Any function of T1 and
It
T2.
can be any function of T1 and T2, but the function should be same. That is what. So function of T should be same. We are taking function of T is to be nothing but is just the same T. That's what. F of
T.
x is just
Okay,
x.
sir.
That
Okay,
is what
okay,
we are
sir.
taking. So basically, you cannot say Q1 is equal to T1. This is wrong. But you can say Q1 by Q2 is equal
That's
to
of.
T1 by T2. This is right.
Okay, sir.
Okay. You cannot simply replace Q1 with T1 or Q2 with T2, but you can say the
Actually,
ratio of heat can be replaced with ratio of temperature, because it's an
okay, sir.
irreversible engine. This doesn't happen if it is an irreversible engine.
Okay, sir. Thank you, sir.
So that is where you can replace QL by QH to be TL by TH. You cannot replace QL with TL and QH by TH. That is
Okay, sir.
so the ratios can be replaced, but not the
Individual
individual Qs.
reservoir.
Yeah. All right. Any other question?
Sir, I have one means doubt in assignment problem.
Sure. Which
Can
problem?
I ask, sir?
Sure, sure. Which
Uh,
problem is that?
in assignment number 8,
Okay, week 8.
assignment number 8 and question number 3, sir. इसका.
Question number 3. Okay. So 1 mole of CH4 is reacted with O2 in stoichiometric proportion. The reactants are at
जी sir.
temperature this and the pressure is this. Use the following data of enthalpy values at reactant conditions. Determine the heat of combustion. Okay. So, what is the problem you are facing?
Sir, I got answer in negative value minus 49.52.
Oh,
But
okay.
in solution, there was taken in formula negative. So I
Mm-hmm.
am not able to understand how negative sign
Okay.
come.
So basically, there are two things, right? So there is something called heat of reaction and heat of combustion. So
Yes, sir.
okay. So heat of combustion is actually positive. Let me show that.
Sir, if possible, please explain in detail because
Sure, 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 sure.
theory and numerical both, sir.
Mm-hmm. Sure. So where is the heat of combustion? Enthalpy of combustion. Exiting combustion product minus reactants. Maybe what I will do is I will solve so that you can understand it easily.
Okay, sir.
So, so you know what is enthalpy of combustion, right? So let me explain that first. So
Yes, sir.
uh, when there is reactions, what happens
Yes, sir.
is, what reaction does is it converts the high energy, you know, uh, Aditya, sorry. Okay. So when there is reactions, what happens is basically you are doing combustion. In combustion, what you are doing is you are converting the high energy, high chemical energy within the chemical bonds of reactants, and you are
Yes, sir.
releasing it as a heat. Okay, so let's say if you take
Yes,
here, you have CH4, which is methane, right? So methane, and you have oxygen, right? So this is the fuel,
okay.
this is the fuel, and this is the oxidizer. So basically
Yes, sir.
what you are doing is the energies, in the methane, because it's a since it's a methane, it will have energies in the
Natural
bond,
gas. Yes.
right? CH4. So what it has is it has some energies within the bond. Now,
Yes, sir.
now if you attack with oxidizer, what you can
Yes,
get
sir.
is CO2 and H2O. uh, yeah, basically CO2 and H2O you can get, which means you are breaking these bonds and you are forming new bonds. So during
Yes.
breaking these bonds, a lot of energy is released.
Yes, sir.
Energy is released, okay, which is which is leading to the increase in temperature. Okay, the energy
Temperature.
which is
Yes, sir.
stored in the bond is getting released, which is increasing the temperature.
Okay, sir.
Okay, temperature keeps increasing. That is how the combustion reaction happens. You are basically converting chemical energy which is within the bond, converting it into the thermal energy, right? The energy
Heat
which we
energy. Yes.
can feel. So basically here what they are telling is they are reacting methane, so CH4 plus oxygen in a stoichiometric condition. So
Yes,
they
sir.
are reacting and they are producing CO2
H2O.
and H2O, right? Now it's a
Yes.
it's a
Plus
stoichiometric,
energy.
it's a stoichiometric condition, which means you need to balance
Yes.
this relation. So you stoichiometric means you are converting all the carbon to carbon dioxide, all the hydrogen to water. Okay, that is what stoichiometry means.
Water.
Stoichiometry means
Yes.
you are fully converting
Complete
all the
combustion.
complete combustion, exactly. So if we do that, um, then if we want to balance, then it's going to be 2H2, which balances H2O. And how do
O2,
we balance this?
O2, go 2 and 3.
So C is 1, H is 4, so this is going to be 2. So you have 2O2, and so this is going to be 2.
2 to multiply. Yes, sir. Balanced.
So this is balanced. Uh, so now you have 1 mole of methane, 2 mole of oxygen, giving 1 mole of carbon dioxide and 2 hydrogen. I
Water.
mean water. Okay. Now upon doing this conversion, okay, what is happening is
Yes, sir.
you have generated some, you have produced some heat. That is what
Molecules.
we have to
Yes.
calculate, right? So what I'm going to do is, you might know this, but I'm just explaining you in a easier way.
Yes, sir. Yes, please.
So you have the CH4 and O2 inside this box, let's say. Okay.
Yes, sir.
Now at the end, so let's say this is at pressure 1 atmosphere, and temperature is, what did they give the temperature? What the temperature? They didn't give anyway. So let's say it is at 300 Kelvin. Okay.
Yes.
Now what I'm doing is I'm converting it into, it's adiabatic, let's say. There is no heat entering or leaving. Okay. Now
Okay, sir.
now it will combust and it will react and it will give me CO2 and H2O,
H2. Yes, sir.
right? Now what would be the temperature inside this temperature of this gas?
Increased. Yes.
Like let's say pressure is constant. Like let's say I have a piston here which can move.
Yes, sir.
Okay. But still it's adiabatic. Okay. Now the temperature
Okay,
will
sir.
increase to a certain amount. We don't know that. Let's say we call it
Yes, sir.
T2. Okay. Now what I'm
Okay,
trying to
sir.
do is I'm trying to get it back to, I'm going to have CO2, I'm going to have H2O, and the pressure is still 1 atmosphere, what I'm going to do is I am going to remove heat Q, okay,
Okay. Hmm.
so that the temperature comes back to 300 Kelvin.
Okay, sir.
So T1, T2, T3. This is first state. This is second state. This is third state. From 2 to 3, what I'm doing is I'm removing Q. Okay.
Means there is not no adiabatic in
I'm
third
removing.
number system.
Yeah. So I am
Yes.
removing this adiabatic, and then so that I can remove the Q, I will remove the Q until it reaches 300 Kelvin.
Temperature 300 Kelvin.
300 Kelvin. So what I will be doing, so this temperature would be very high. Temperature would be higher than 300 Kelvin.
Yes, sir. Hmm.
Now, since I removed Q, how much is this Q? That is what heat of combustion is. Okay. So I start from P1 and T1, which is 1 atmosphere 300 Kelvin.
अच्छा sir.
I combusted it, and then because of combustion
Okay,
temperature
sir.
has
It removed by the system.
I
मतलब it is
removed it.
from the
I
system.
removed it from
Yes.
the system. So how much amount of heat I
Okay.
removed?
Negative.
Okay, it is negative, but in terms of system. So if I say heat added to the system, then it is negative. But heat of combustion is nothing but amount of heat I removed, right? It should be positive. That is
Okay,
what
sir.
it means. Okay, heat of reaction is negative, because from here to here if you go, you are generating lot of heat, right? So H of products minus H of reactants is going to be negative, but heat of combustion is positive, because heat of combustion is amount of energy you are generating because of combustion. Okay, because of combustion, how much amount of heat you are getting. Okay, so it will be positive. That is what this means. How much amount of heat you are removing. If you see in terms of system, it will be heat of reaction, which will be negative, as you said. So that's why you give in terms of
Yes,
negative, but actually what they asked
yes,
were
sir.
heat of combustion. So let me show that to you.
Combustion.
Where is that? So there are two things.
Yes, sir.
Enthalpy of combustion. Enthalpy of combustion. So basically here, I think you are able to see. So this part, right? Heat or enthalpy of combustion. Enthalpy of combustion is MEHE products minus reactants. Exiting
Yes,
combustion
sir.
products minus reactants. So these are at same temperature and pressure. So did sir solve some problems related to this? I guess.
Sir, in assignment solution have been given in that. We can source a direct solution of that assignment problem.
Which one? Assignment solution. Oh, okay, here it is.
The assignment solution.
So if it is products minus reaction, it should be negative, no? Why it is it positive? I don't know.
Sir,
So
here
here they have written.
taken negative side.
Okay, so here the enthalpy of combustion, heat of combustion is reactants minus products. Uh, Delta Hc divided by molecular weight. See, this is it's 50.2. It's positive, right?
Yes, sir. I have problem at this place in formula, sir.
Okay,
And
in
that
formula.
heat of combustion is a ratio of heat of reaction by molecular weight of fuel. That is right, but why we are taking negative sign before the heat of reaction?
Right. So the heat of, as I said, the heat of reaction is, it will be negative. Heat of reaction is negative, but heat of combustion is negative of heat of reaction. Because let me put this in way. So until here you are clear, right? So this say 803.5. Shiv? I think you are. Huh. So until here you are clear, right? 803.5 kilojoules per kilomole.
Yes, sir. Yes, sir.
So that is heat of reaction, right? The change in enthalpy.
Yes,
So basically, reactants will have higher enthalpy, products will have lower enthalpy, and that is what giving us heat,
mm,
right? So basically, this is negative. This is heat of reaction, but heat of combustion problem
yes.
formula is negative of heat of reaction. Okay, basically it is H of reactants minus H of products. H of product minus reactant is the heat of reaction, but heat of combustion is positive.
Certainly, but we are means heat of combustion is releasing from the system.
Heat of
So
reaction is
why
releasing from
not
the
we are
system.
taking negative side?
Heat of reaction is, so upon heating,
Like heat of combustion is that of heat we found from the system because that time this one is not adiabatic system. We are saying that heat is removed from the system.
right? So let me go back to this. This is heat removed from the system.
Yes, a three number system
Uh, this Q is, this is from 2 to 3, right? Heat removed
from the system is
from
heat
the
of
system.
combustion.
This is negative. And how do you find this? This is nothing but summation of H of products. You can simply write H of products minus H of reactants, right?
Yes,
Now this is heat removed from the system, and how you are getting this heat? Through reaction. So you call it enthalpy of reaction. But from a combustion perspective, what you are interested? We are interested how much amount of heat I can gain from a combustion system, right?
this is
So let's say if you are using it, where do you use it? Let's say from an engine, upon combusting, you will generate lot of heat, and that heat, what you are doing is you are heating it to heating the steam. Let's say you are converting in a steam engine. What you do is you will generate lot of heat, and using that heat, you will convert water into water vapor. Let's say you are boiling it, right? So
yes.
for that, what you need? You need heat, right? So and that heat is coming from combustion. So how much amount of enthalpy I can get from a combustion is nothing but delta Hc is nothing but negative of delta Hr. The reason is you are going to use that heat for something else. That is why this is called enthalpy of combustion. It is just convention. That is how they define it in a
Yes,
that is how they define it. Upon reaction, you get enthalpy of reaction. So upon doing this process, I am going to remove it. That's why it is negative, right? But I am going to use this heat for something else, and that's why we call it enthalpy of combustion, and we are telling it is negative of enthalpy of reaction. That is what you see in the here. So you see enthalpy of combustion and heat of combustion are same, which is nothing but negative of heat of reaction. heat of reaction is product minus reactant, and since you put negative, you'll get reactant minus product. That's it. Okay. So this is a this actually doesn't have any physical meaning, but this is the convention they
Yes,
follow.
sir, sir. Only this question is wrong in my assignment, but
Okay.
I got full marks. But in this question only, because I saw a solution in Pekenak thermodynamics, sir. So there was given in negative that
Yes.
heat of combustion.
1 minute.
That's
Give
why
me a minute.
I follow that notes or that book. Yes,
Okay. Give me a minute. I will check in Stephen turns. I'm sure that it should be positive, but give me a minute. Huh?
yes, yes, sir. I understood why it is coming positive.
Hello. Ah. So
Yes,
basically, Stephen turns is the books suggested for combustion.
sign convention. Yes, sir. That is sign convention taken by different author.
Mm-hmm. So sign convention is taken by different authors, but
Yes,
I think they will, in the course, it is true actually. Whatever you said is true. It doesn't make sense, just for negative you are
it is
giving, you are not getting marks for this.
marks.
Yeah,
Yes, sir.
but
Yes,
you understood the concept, right? So that is what is
yes, sir.
important.
I understood the combustion.
So
Because of combustion, we got heat from the combustion.
true, exactly. That is, yeah. So let's see. It is, yeah, it's a matter of convention. That's what it is. So heat of combustion is also known as heating value. So whenever, let's say, you are burning, diesel, right? So when you burn diesel, they will see that this much amount of energy I can get from you know, this much kg of fuel
Yes.
or liter of fuels, right?
Mhm.
So that is what they do, numerically equal to, but with an opposite sign. So in Stephen terms also they follow the same convention as,
Okay, sir.
I think PK Nag
Sir,
followed.
shall we get marks or not? That will be wrong. Sir. I got
Actually,
minus 49 point.
I understand. It's
Yes.
right. So basically, what Stephen R. Turn says is enthalpy of reaction is products minus reactant, which should be negative for sure,
Yes, sir.
and enthalpy of combustion is negative of enthalpy of reaction. So basically, it should be positive. That's what they say. So, and that is what the convention they follow in in our lecture also. So I
Yes,
don't
sir.
think so they will provide you marks for this,
Okay, sir.
but forget about the marks, it's fine,
Yes, sir. Yes, sir.
but you understood the concept, is that is what is important.
Yes, sir. Yes,
So
sir.
but this is
Yes, sir.
the
If
kind,
possible, yes,
is
sir.
PK Nag, do they follow opposite convention, are you sure?
Yes, sir. Yes, sir.
Okay, so do check
If you
once again.
can you consider, sir, a one time you convey, please convey this message to your kids, sir, if possible.
See, I can do it, but what you can do is, if the request is from you, then it would
Yes,
be
sir.
more, they will consider it little carefully. So if
Sir,
the request is
I
from,
mail for this means question,
so
but
whom did you mail?
ask it, uh, ma'am or some ma'am I have to solve this one.
Okay, so did you raise this issue in the common forum?
Kavita Nayak ma'am.
I see. So
Yes.
did you get any response? So
Yes,
okay.
yes, sir. She said that she follow different book name.
Mm-hmm.
And the yeah, yes, sorry, the heat of reaction is taken negative based upon the formula mentioned
Mm-hmm.
in the book. Kindly follow the book properly. For more details, go through the attached file. Follow the book and introduction to combustion and concept by Stephen R. Tudd.
I see.
They commented by.
I see. Then I don't
Yes.
think so we can do
But
anything,
sign
Shiv.
convention different for different book.
So actually, what is the case is this is the
Yes, sir.
usually heat of combustion is called heating value. Okay, and in every
Yes,
place,
sir.
what they do is they use this convention only. I'm not sure why PK Nag used this.
Yes, sir.
So that's what. So basically, in every research papers and other things also, they follow
Yes, sir.
this convention only. So it is also same like heat
Okay.
is entering the system, heat leaving the system convention, right? So if heat
Yes, sir. Yes,
enters
sir.
the system, we call it uh, positive, and heat
Positive.
leaves the system, we call it negative. So
Okay.
similar convention is
Negative. Yes.
actually it's universal for heat of combustion and heat of reaction. But I'm not sure
Yes.
why PK now followed, and since that is not recommended book for this course, I don't think so it is possible. uh,
Okay, sir. Okay, sir. Thank you. No problem, sir.
yeah, but you understood the concept, that is what is important. You understood it,
Yes, sir.
right?
Yes, sir. Yes. Yes.
Okay, all right. So is there any other questions you want to ask, Shiv?
Sir, can I ask from advanced IC engines like RCCI engine? Probably.
uh, so basically my specialization is in uh, aircraft and rocket combustion, propulsion and combustion.
Okay, sir.
So I'm
Rocket
not sure whether
propulsion.
I can answer, but you can ask. If it is a basic question, I will be able to answer. So my specialization is
Yes,
in
sir.
combustion and
Sir,
propulsion.
as we know, RCCI engine reactivity controlled compression.
Reactivity controlled.
Yes, sir. Yes, sir. Sir, maybe you can. Sir, in RCCI engine means reactivity control. Yes, sir. And one is your SCCI engine, that is homogeneous combustion. How many? Homogeneous charge compression ignition engine. Sir,
Homogeneous
in
charge
both what, like, sir, my question is that in dual fuel engine,
Mm-hmm.
we are using two fuels.
Mm-hmm. Okay.
In dual fuel, we are using two fuels, and in RCCI engine, also we are using two fuels. But
Okay.
in RCCI engine, we change only that one fuel is high reactivity fuel, and one is another is low reactivity fuel.
Mm-hmm.
So, how can we differentiate RCCI engine and dual fuel combustion?
I see. It is new to me actually. I have no idea about any of these engines.
Okay, sir.
So what is RCCI engine?
Okay, sir. Thank you, sir. Thank you, sir. It's okay, sir. It's okay.
It is fine. So yeah, I'm not sure. I sorry I couldn't help.
Yes, sir.
Uh, I'm not sure what are those engines actually.
It's a thank you, sir. It's okay,
No
sir.
problem. Okay. So do you have any other
Okay,
fundamental
sir.
doubts?
So, sir, no, sir. Last basically, sir, I joined this course for only that combustion part, advanced combustion part
Okay,
of
okay,
this,
okay.
because I am doing PhD in combustion field. Yes, sir.
I see.
Engine combustion field. So,
Which
so I am
institute
reading,
you are
sir. If
studying?
faced any problem before exam, so I will ask, sir. Yes, sir.
Which institute you are in?
Sir, I am not from RGPB, UIT RGPB, Bhopal.
Okay, okay, okay. So, but basically,
Yes, sir.
this course is, advanced thermodynamics, but combustion is still preliminary. This is
Okay, sir.
a basic combustion course. In fact, we did only for, you know, we
Yes,
started
sir.
in the
Sir.
middle of the course, and
That was very interesting course, sir. I enjoyed this course because of that combustion parts.
ha ha ha. So, but still, it's a very
Hello.
preliminary. So, advanced
Yes, sir.
combustion topics are, like diffusion flames and laminar flames is where all these things will come. Uh, but that part is very much limited
Yes, sir.
textbook. So probably, let's say if you take a CI engine
Yes,
or
sir.
SI engine, you are doing engine combustion. So there you will have
Yes, sir.
CI engine
Advanced
would be
combustion. Yes, sir.
CI engine would be like a diffusion flame, droplet combustion. Those things would be more. In SI engine, it's a more
Yes.
remixed combustion, right? So uh,
Yes.
those things are has to be dealt in detail in advanced combustion courses, but it is
Okay, sir.
it is very difficult to find any advanced combustion courses. So only if you are
Yes, sir.
uh, maybe what you can do is, what I would suggest is, you can look for you know um, some professors in IITs or NITs, wherever,
Yes.
who works on these fields, and
Yes.
you collaborate with them, so that then you can ask this kind of specific high, advanced combustion questions to them, and they will be able to help you. Okay, so
Okay, sir. Okay, sir.
there you
Thank you,
will
sir.
find it. So my field is more related to solid propellant combustion, homogeneous
Rocket. Yes.
rocket combustion, and also I also do a little bit about premix combustion, gas turbine based combustion, and I have very little, or no idea about CI and SI engine
Okay,
even.
okay, sir. Okay, sir. Okay, sir. Yes, sir.
uh, all right. Any other
Yes, sir.
questions you wanted to ask? Shiv?
Sir, I have no problem, but night time still I have to study all those like combustion and thermochemistry of that part.
Okay,
I
okay,
don't got time to then night time I have no any doubts.
okay, okay, okay. All right. So that is okay.
If you are revising, sir, means that course. So, if possible, sir, after week 8, from week 8, if in short time, because this means this program is up to 9 p.m. Na, sir.
Yeah, 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 yeah. So
So,
you
sir,
want
in
me to
short,
revise from
if
week 8, right?
possible,
Okay.
week 8, sir. Yes, sir. In
So what I
short,
will do is,
means
I will quickly go through the other, for
if
continuity,
you
for the sake of continuity, I will quickly go through the previous weeks also,
yes,
and
yes,
then we
sir.
can
Yes, sir. Yes, sir.
briefly discuss combustion from week 8.
Yes, sir. Yes, sir. Yes,
All right.
yes, sir.
All right. So and then
Yes, sir. Yes, sir.
we started second law of
Yes.
thermodynamics. In second law of thermodynamics, we know that there are two statements: Kelvin Planck statement and Clausius statement. And
Yes.
and then Kelvin Planck statement deals with heat engine, Clausius statement deals with refrigerator and heat pump. And we also looked into Clausius theorem, and we said for any reversible process, let's say if you have a reversible process,
Power
then
on.
uh, you can develop,
Device paired.
you can uh, find we define something called entropy here. And entropy, entropy is also a state function, so which means dq by t, even though q is a path function, this dq by t will be a state function, and that's why it doesn't depend on path. So let's say if you have any initial and final state, and let's say you are going through any process, you can replace it with a reversible process, and you can find the entropy change during that process, and that process entropy change will be same as the irreversible processes entropy change. And that is something. And then we derived it, we use this TDS equations, um, and then we derived for entropy what are the relations, and then we studied a little bit about Clausius inequality and how it can be useful. And then finally when we did for entropy balance, we came up with some, let's say there is some entropy change. The entropy change could be due to entropy production also, because of irreversibilities happening in the system, boundary irreversibility. And then uh, we also wrote entropy balance equation for a closed system and also for a control volume. Basically, first law of thermodynamics, energy balance. And from second law of thermodynamics, we wrote something called entropy balance. And then we looked at isotropic process, and let's say turbines and nozzles, how they work, and entropy balance we can quantify. So that is what we said. And then polytropic process, for that also how work has to be performed, and those things. And then exergy analysis. So basically entropy analysis we had, and in
Hello.
exergy analysis we will have exergy balance.
Yes, sir.
There is some echo from Shiv, I guess. Let me mute. Whenever you have question, you can unmute yourself. Sure. So we have exergy analysis, and we had exergy balance also. Exergy balance. Basically, exergy is for a closed system plus a immediate surroundings. So that is how we defined exergy. So entropy contribution also comes into picture, and uh, and then we define something called second law of efficiency, which is going to tell with this which is the more efficient way, which gives lesser entropy change, or in which you will have use lesser amount of exergy. So the concepts we studied, and then thermodynamic functions. So Maxwell's relations we used. The Maxwell's relation, it actually relates PV and T with SH and U. Here S, U and G. S, U, G, H. Okay. So it will be helpful in various processes when we want to quantify. When everything is calculated in terms of, in experiments we calculate pressure, temperature, volume change, and those things. But if you want to get entropy change, Gibbs free energy change, those things, it would be difficult. So that you can calculate using Maxwell's relation. And for phase change process we did Clapeyron equation, and then we introduce ideal gas assumption to get Clausius-Clapeyron equation. And we also discussed about phase diagram. There's going to be phase diagram is in P and T, and phase change, there is this solidus line, liquidus line, fusion curve, you know um, those sublimation, evaporation happens across this curves. So that is something. And then property evaluation, let's say if you want to calculate properties, there also we use Maxwell's relation. And then yeah, internal energy is one of the property we would like to evaluate. And then there are a few thermodynamic equations which we use for various this thing, uh, places. And then we have TDS equations, and then um, there is a different way of finding amount of heat required for isothermal change of pressure in a fluid substance, reversible isothermal change of pressure. So it can be either found by what is the amount of change in pressure and temperature, but it can also be found with a different methodology. That is what we have here. And then Joule-Thomson coefficient for refrigerator and air conditioning systems. the throttling process is essential. There you will have Joule Thomson coefficient, and we have this inversion curves, and you want your inlet to be on the right side of the curve, and so that upon you know the throttling you will have increase in temperature. So that is the reason we have this. So those are
Sir,
something.
hello,
Yes, sure.
sir. Sir, one problem I have in Clapeyron equation
Mm-hmm.
in previous sir, uh, at the time of phase change,
Mm-hmm.
that is dp by dt for that it is only for saturation point is given.
Mm-hmm.
So for saturation, sir, how we change pressure or temperature? Means for a change of a phase, temperature is constant. So how we are differentiating with respect to temperature at that point?
So basically the reason to use Clapeyron equation is, let's say you have, so during phase change process pressure and temperature doesn't change, as you rightly said. Okay.
Yes,
Now
yes,
during then you will have, where do we have that another curve? There will be one more curve. So this curve, if you focus this curve, okay.
yes,
So during this phase change there is no temperature and pressure change, because temperature is constant along this line,
yes,
pressure is also constant along this line, and
yes,
for this you need some HFG,
yes, sir.
right? Now,
Vaporization,
uh,
effect of vaporization.
now let's say you increase the pressure and temperature. Let's say you are in this region, okay.
Yes, sir.
Now the HFG is different, right? The amount of energy required for phase change is different, and
Yes, sir.
calculating that is calculating the, you cannot do experiments for every pressure and temperature, right? To calculate the amount of
Okay, sir.
H required, right? So let's say for some value, for some let's say at a P at 1 atmosphere and temperature at 373,
Yes,
let's say you know what is the HFG,
yes,
what is the latent heat required for evaporating, okay. And let's say
yes,
if I increase the pressure from 1 atmosphere to 2 atmosphere, okay, then
yes,
the saturation temperature also increases, right? This saturation temperature also increases because my pressure has increased, right?
hmm, hmm,
uh, so for a given P and T, what is the enthalpy required? So that is what this
yes,
Clapeyron equation tells us. Okay, it doesn't tell about the process, how the phase change happens. Let's say if you want to quantify HFG here, right? So
yes,
you can draw this line using experiments. From experiments, you will know P and T curve, right? So let's say liquid to vapor you are moving, okay. You can draw this line P and T, right? But during this change you need to know how much energy you require to change liquid to vapor, right? But so
okay,
let's
sir.
say this is 1 atmosphere. At 1 atmosphere you know H of G is some kilojoules, but at different
Yes, sir.
atmosphere, at two atmosphere we don't know
Yes,
how much H of G is, right?
yes, sir, yes, sir, yes,
But
sir.
we know P
100% sir,
sat and
yes,
T sat,
yes,
right? Then you can put it in this
yes,
equation to find amount of heat. So these are two different
okay, sir.
processes, that's what I'm trying to say.
Okay, sir.
Okay, so it relates
Understood,
the
sir.
saturation pressure, temperature, and the HFGs and VFGs. Okay, so this kind of relation will be helpful
Okay, sir.
when we don't know some of the things, and we know some of things, but we don't know other things. And if you want to quantify it, you can use Clapeyron equation. That is the
Thank you, sir.
yeah.
Yes, sir. That was my basic part before in means graduation time, but today I got clear, sir. Thank you, sir.
All right.
And sir, one question, another question is, sir, we are noticing triple point having 0 degree of freedom. So why we are calling 0 degree of freedom at triple point having 0 degree of freedom? Because to denote or to means so triple point we have need of one temperature point and one pressure point. So hot zero मतलब degree of freedom is zero for triple point of water. Yeah, anything sir.
Okay. So any system you can modify it like this, right? So let's say you have some mass within a container, and you can increase the pressure and temperature so that its volume increases or decreases, right? That is what the degrees of freedom. So you have
Yes,
two degrees of freedom. You can increase either pressure or you can either increase temperature. That is the degree of freedom. uh, and during this
yes
degree
sir.
of freedom,
Mm.
the system interacts with the surrounding. It can gain energy, it can release energy, all those things can happen. Now you are telling that we want to have both solid, liquid and vapor in the same pressure and temperature,
Yes sir.
right? So when we want these three at equilibrium, which is triple point,
Mm.
we cannot change anything. So let's say pt, then it will not be in equilibrium. That's what whether I don't know whether I conveyed it properly. So in a triple point, what happens is all three coexist together:
Yes sir. Mm. Mm.
solid, liquid and vapor, water vapor,
Yes, yes.
right? So now if you change this, let's say if you change the pressure, these three things cannot
Yes sir.
coexist together. That is the reason the triple point is, you know, it doesn't change. So and also you can check like this: there is this curve and this curve and this curve, and all three curves can meet only at one point. It cannot meet at another point,
Yes sir. Mm. Mm.
right? So this peculiar state can happen at 1p and 1t.
Yes
It
sir.
cannot happen in any other p and t's,
Yes sir. Mm.
right?
Sir, means degree of freedom is defined as we know. मतलब how many equations are required to define any means ये. So at that at people point I have we have need of two temperature means temperature is fixed, that is one is 273.16 Kelvin. So we have need of one temperature and one pressure also, but degree of definition of degree of freedom is another thing.
So yeah, I
By Gibbs
understand.
law, by Gibbs law we got degree of freedom is zero by
Right,
Gibbs law at that point.
right.
But physically, I am not understanding how we can say that is degree of freedom having zero degree means a triple point having zero degree of freedom.
uh, yeah, whatever you said is true. So basically any
Yes,
system can be defined by two states like p and t, right? uh, only
yes,
when you
sir.
define these p and t, you can define all the other things like energy, other things, right? But for triple
Yes, sir.
point, there is no such definition. It can happen only at one point. That's why it cannot have any degrees of freedom. Which means that at triple point we know all the properties, including internal energy, entropy, every other property,
Yes, sir.
temperature, pressure, the specific volume, everything we know, and it cannot change anymore. Okay. But for other states, let's say if you are let's say if your system is phase change from liquid to gas, I can have uh,
Yeah.
I can I then I will have 1 degrees of freedom. The reason is I can change the saturation pressure or saturation temperature, right? So if I
Yes, sir.
increase
Yes.
the saturation pressure, temperature automatically change. We are not changing the temperature,
Yes, sir.
right? So phase change system has 1 degree of freedom,
Mhm.
like either pressure or temperature. But triple point
Yes. Yeah.
doesn't have 1 degree of freedom or zero. It has only 0 degrees of freedom, which means you cannot change p and t. It exists in only one particular p
Sir,
and t.
okay, sir. Okay,
So
sir.
that's why it is not so uh, you no need to define p, you no need to define t. All are product of uh,
Constant unknown.
product of the system. So let's say for example, you have phase change system. It happens at some saturation pressure. Then once you
Yes,
know
sir.
saturation pressure, you can get saturation temperature, you can get hfg, you can get what is the amount of you know uh, uh,
enthalpy, heat, and rate.
enthalpy, entropy, everything you can get. These are product of this, right? So since you fix the saturation pressure, you will get all these things, right?
Yes.
Similarly, for a triple point, you no need to fix anything. It is already fixed. P, T, and
Yes.
everything else is already fixed. That's why we say it's a 0 degrees of freedom, because it cannot exist in
Yes.
any other pressure and temperature. It can exist in only that pressure and temperature.
Okay, sir. Okay, sir.
So,
Right, sir. Right, sir. Okay, sir. Thank you, sir. Thank you.
all right. So let me go through liquefaction gives rise to this, and then we saw equation of state, ideal gas is zero, right? And then we come to a mixture. The reason to work with mixture is uh, because in real systems, let's say for example air, it's a mixture, right? It contains H2, it contains water vapor, it contains oxygen, it contains nitrogen, it contains xenon, all minor compositions of carbon monoxide will be there, ozone will be there, all these things will be there in air, which is a mixture. And that's why we need to study a little bit about mixture. And even in combustion systems we deal with mixture of fuel and oxidizer before, and then and in the product side we will have a lot of things, right? So that's where we defined there are in various ways which you can define a mixture. Usually in partial pressure law we use, where we will add partial pressures of each and every component in the mixture, and we get the pressure of the gas. And so we define certain properties, partial molal properties. So X's can be any property, any extensive property. If you want to define partial molal property, you will define it something like this. And then chemical potential we define Gibbs free energy. Gibbs free energy, it is coming from, uh, you know, from the entropy TDS relations. We have H is equal, U is equal to H minus V. Yes.
Yes, sir.
Okay. So basically
Sir,
we
please continue.
okay. So we have internal energy to be H minus V, enthalpy to be Ts. So this is how we define it for mixture, right? So
Okay, sir.
and then we have Gibbs dual equation. We define fugacity, and but we didn't actually use this anywhere, but it is in you usually use it in combustion system. So both chemical potential and
Okay, sir.
fugacity we use it in the combustion system. So but this is not dealt in detail in this course. So right.
Okay, sir.
uh, and we have ideal gas mixture law, right? So ideal gas, it can be uh, we are extending ideal gas law to gaseous mixture. And then we what basically the ideal gas law tells is there is intermolecular forces are negligible, which we already know. And then we define partial pressure as Ni r bar by V. And then uh, that is how we define other quantities also, summation of yi, right? Yi's are mole fractions. If it is a mole fraction, then this will also be a molar quantity, so please remember that. If it's a mass fraction, then it will be a mass quantity. So let's say for internal energy can be kilojoules per kilomole or kilojoules per kg. So if it's in kilomole, then you need to multiply with mole fraction. If it's in kg, you need to multiply with mass fractions. That is those are the things we did in the mixture. And then we discuss combustion. So in combustion, the important things are, first thing we discussed was about adiabatic flame temperatures and heat of combustion, heat of reaction. So from combustion, what we are trying to attain is we are trying to get some energy out of combustion. Basically, energy is stored in form of bonds. Upon dissociating that bonds are, let's say, in any fuel, you will have petrol, diesel. Those are all uh, complex molecule which has a lot of bonds in it, and upon breaking that bond, you will release energy. So that energy is actually felt as an what do you call sensible enthalpy, which is being used everywhere. Let's say, for example, if you take a CI engine or SI engine, you are converting that energy within petrol and diesel into heat energy, which is then converted into mechanical work by the motion of piston. Right? So basically, you are converting chemical energy to a thermal energy, and then thermal energy to a mechanical energy. That is what is being happening in the engines. Uh, the combustion deals with how to convert this chemical energy to a thermal energy. That is what this combustion deals with. So how much amount of energy you can get it from combusting a fuel? From there is, let's say, there is a reaction between fuel and product, fuel and reactants, sorry, fuel and oxidizer, and after this reaction you will form some products. So during this process you will take heat out of the system. That is what the combustion process does. So uh, to define its performance, we define something called heat of combustion, delta Hc, and which is nothing but heating value of any uh, you know what do you call the fuel, heating value of any fuel. And then we have adiabatic flame temperature. These two are different places where you how like these are the things which is going to quantify the performance of that fuel for as a like for combustion. Okay, so enthalpy of combustion or reactant is nothing but you are trying to combust the reactant and fuel from its initial state to a final state, but the pressure and keeping pressure and temperature constant. So basically in a combustion process, we already know. So I'm just minding this. So this will be, let's say, reactants, and this will be products. This is, let's say, total enthalpy. So in any combustion process, what happens is you will have some enthalpy in it. Okay, and in that you will have some sensible enthalpy in it, and you will have a lot of latent not latent, the formation enthalpy. So this is the formation enthalpy. Formation enthalpy means nothing but the enthalpy stored in forms of bonds within chemical bonds within the fuel, right? Formation enthalpy. And this is blue color is sensible enthalpy. Maybe I will draw it separately. Formation, this is sensible. So in reactants you will have lot of formation and small sensible, and for products, you what you did was you converted all the most of the formation enthalpy into sensible enthalpy. So basically, sensible enthalpy is the enthalpy which you feel, like it can be sensed. So basically, how do you sense an enthalpy? It's based on temperature, right? So what you did was, here both have same enthalpies. Both reactants and products will have same enthalpy, but what you did was you increased this composition, and because of this the temperature has increased. Sensible enthalpy is nothing but, crudely speaking, is CPT, right? Here it will be CPT of reactants, here it will be CPT of products. Since sensible enthalpy is more in the products, this T of products is also called as T adiabatic flame temperature, and that is how we get adiabatic flame temperature. Basically, it is coming from energy conservation. So initially, I have this much enthalpy, and this much amount of formation, this much amount of sensible, and I am converting it into some amount of converting it into a low energy species, let's say like products, which has lesser formation enthalpy. So high formation enthalpy reactant to low formation enthalpy product you are converting, and during this conversion sensible enthalpy has increased, which is giving rise to adiabatic flame temperature. Let's say if you put everything, that's why it's called adiabatic flame temperature. Reason is if you put it inside the adiabatic container, if you put reactants and products in it, and if you uh, allow it to combust, at the end the temperature would be adiabatic flame temperature. And this is for a constant pressure process, which means that system, if there is a increase in pressure, it will accommodate, let's say a piston cylinder arrangement, right? So for a constant pressure process also you can define adiabatic flame temperature, or you can also define adiabatic flame temperature for a constant volume process, right? So constant volume process adiabatic flame temperature would be even higher than constant pressure adiabatic flame temperature. The reason is you are going to have, you spend some energy in a constant pressure process to move the boundary, which means some work has been used. That is the reason you are going to have uh, adiabatic flame temperature. And uh, basically we compare enthalpy of reactants and enthalpy of products to get this get the adiabatic flame temperature. And heat of combustion and heat of reactions, we discussed it already.
Sir,
And
sir, my
yes,
connection was lost, sir. Can can you, sir, tell about adiabatic flame temperature?
right. So
1 minute. Right.
sure. So are you did you understand this analogy what I am trying to say?
Yes, sir. Yes, sir. I understood reactant and products that sensible and formation energy.
Okay.
After that, what is मतलब exactly a diabetic flame temperature? Is
Right.
temperature of flame? Right.
Ha ha. It is not exactly temperature of flame,
Not
but I'll
exactly
give you.
temperature of flame. Yes, 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 yes.
So here is where your fuel and
So here is
oxidation
where
is.
your fuel and oxidation is. Yes, sir.
It is at T reactants,
These are key reactions.
300 Kelvin. Okay.
300. Yes, sir.
Now this is adiabatic
Now
container.
this is adiabatic temperature. Yes, sir.
Now, if you leave it
Now,
like that,
if you
what
leave it
happens?
like that, what happens?
It forms products,
Comes water. Yes, sir.
and this is still adiabatic, so
And
there
it
is
is
no
still
heat
adiabatic,
lost
so
from the
there is
system.
no heat lost from the system. Yes, sir.
Okay. Now, what is the temperature?
Now, what is the temperature?
It would be
Okay,
greater
sir.
than T reactants.
It is greater than the reaction. Yes, sir.
This temperature is called adiabatic flame
This
temperature.
temperature is called adiabatic temperature. Okay, sir. Okay, sir. Okay, sir.
So the temperature with which
Understood,
it
sir.
reach for
Temperature
complete
with which
combustion
it
of
reach
fuel and
for complete
oxidation.
combustion of fuel and oxidation. Yes, sir.
Now this can be either a constant
Now, this
pressure
can be
process,
either a constant pressure process
or it can be constant volume
or
process.
adiabatic process. Yes.
Okay.
Yes, sir. Constant volume in petrol engine and constant pressure in diesel
Exactly.
engine.
Right.
Exactly.
So let's say if you,
Uh, if you
so this will be in a piston cylinder
will
arrangement.
be in
It will be
the
still
arrangement,
adiabatic.
still adiabatic. Yes, sir.
So pressure will be constant across this, pressure
Pressure will
1
be
and 1.
constant of pressure
So
1 and
here
1.
both the places,
There
before also there
both
will
the
be fuel and
places
oxidizer,
before
and you
also
converted
fuel
into
and oxidizer converted into
converted into products.
converted into product.
So here
Yes,
the
sir.
temperature would be 300 Kelvin.
Here the temperature will
Here
be
the
300
temperature
Kelvin.
would be T
Here the
adiabatic.
temperature will be 3 adiabatic.
This is
Okay,
still
sir.
at T80 energy.
Let me
These are all in adiabatic condition. So this is constant pressure process.
Okay, sir.
And you can consider this as a constant volume process.
Okay, sir.
So there will be two adiabatic. Basically, there are two adiabatic flame temperature. It can be constant volume adiabatic flame temperature, constant pressure adiabatic flame temperature.
Okay, sir. Okay, sir.
That is what the adiabatic flame temperature is.
Okay, sir.
Basically, it's a measure of how much amount of heat you can get it out of a combustion system, or
Hmm.
that is what it means. It's like how energetic your combustion system is, your fuel and optimization. More
Yes.
heavy adiabatic, better your combustion system is, or more energetic your combustion system is.
Yes, sir. That means maybe complete combustion or stoichiometric combustion.
Not exactly. This just tells you uh, what is the temperature you could reach, ideally speaking.
Okay, sir.
But in reality, you will not reach this temperature because uh,
Okay, sir.
if you do a stoichiometric usually complete combustion doesn't happen. If you
Okay,
have a
yes, sir.
complete combustion but without heat loss,
Yes, sir.
then you will reach this
Then
pre-adiabatic. But
Kelvin
in
Planck,
reality, you
Kelvin
will not
Planck.
have.
Yes, yes, sir.
Okay. So that is what adiabatic flame temperature is. And similarly, the
Yes,
heat of combustion and heat of reaction we already discussed. It's
yes,
nothing
sir.
but you have to go one step further. From 1 to 2, you go to 2 to 3. Where you get back from T
Yes, sir.
adiabatic, you come back to T initial, which is T reactants. Upon coming back, what is the amount
Yes,
of
sir.
energy you are releasing is what heat of reaction is. And
Heat
the
of
negative
combustion.
of that is heat of combustion. That is what it means.
Yes, sir.
Okay.
Yes, yes.
So these two are like a characteristics, or these two are like uh, what do you call performance characteristics of a combustion system. Okay, like how much amount of energy content you have within the system is what these two things tells.
Okay, sir. Yes, sir.
So let's say if you come up with a new blend of engines, let's say like you mix petrol and diesel, and you are burning
Yes,
it with air, let's say. For that, if you want to quantify and if you want to say that this fuel is better, how you will say is you will compare these two parameters. One is heat of combustion and
okay,
adiabatic
sir.
flame temperature. You will compare these two parameters to say this is better and that is better. That is how. Uh,
Okay, sir.
that is where these two things are actually useful. It's not exactly like there will be flame and flame will have that temperature. Usually flame may not reach adiabatic flame temperature. Ideally it should reach, but because of heat losses and these products which they form, CO2 and H2O, at since the temperature is very high, they will not remain as CO2 and H2O. They will decompose into
Okay,
CO,
sir.
they will decompose into OH, H, O2 will form, NO they will form. So all these things can form
Yes, sir.
in there, which requires some amount of energy. Let's say if you have CO2, you want
Yes,
to divide it, right? CO and O. For that, it
yes,
requires some
yes, sir.
energy. So these are called what do you call? I think decomposition, I guess, right?
Okay,
So
sir.
these reactions require some energy. These are endothermic energy. So because of that, the temperature will not reach adiabatic flame temperature. It will be little lesser than adiabatic flame temperature. That's why the word
Yes, sir.
adiabatic is also in it. If it's an adiabatic system, then you will reach this temperature.
Okay, sir.
Uh, and then I think I skipped a lot of things. Let's go to where in the from week 8, right?
But sir, I got many benefits from this session
Oh, thank you
because
so
my
much.
some basic concept has been clear.
Thank you. I I'm happy that you are getting help. And one more thing is chemical equilibrium calculation, right? So, uh,
Yes,
basically, this is not detailedly discussed in this course, but let me show you how it can be done. Let's say you have um, some fuel. Let's say you take what you call propane, C3H8. Okay, so propane
yes,
reacts with air. Let's say O2 plus 3.76 N2.
and two.
Okay, some number. Okay, now upon reaction, what happens is, it, as I said, it is going to reach high temperature. What are the products you will get? You will never know, right? So it can form CO2, it can form CO, it can form H2O, it can form H2, it
And
can
two.
form H, it can form O, it can form O2, it can form N2. There will be
That
N2, it
project,
can form NO, it can form NO2, it can form O3 also. There is no guarantee it will not form. And
sulfur
there are
oxides. Yes,
exact. So
yes,
let's say if you have sulfur in the you know
fuel.
oxidizer, it will form that also.
Yes,
Basically, if you look at it, you have C, H, O, and N
yes, sir.
in like four atoms. And let's say if you try to balance
Yes,
it, you can never fill these things, right? Because you have a lot of unknowns. You have 1, 2, 3, 4, 5, 6,
yes,
7, 8, 9, 10, 11. 11 and plus 11 plus
yes,
unknowns you have.
yes, sir.
But the equations you have is only four. You can write equation like
Yes, sir.
there are three carbons here, which is equal to one carbon plus some a. Let's say you write a b c d. So
Yes, sir.
a carbon plus b, something like that you will write for a. This is for c. For
Yes,
h
sir.
you will
Yes,
write
sir. Yes,
similarly.
sir.
For o you
Yes, sir.
can write these things you will write. So you will have only four equations, right? But there are a lot
Yes,
of
sir.
unknowns. You cannot find this, right?
Yes,
So that is where we do something called equilibrium calculations. The reason is, at very
yes,
high temperature, at very high temperature, this CO2 is going to dissociate and form CO and O. Okay. Similarly, at
yes, sir.
high temperature, this H2O is going to dissociate and form H2O2 or H2O. There is one more called OH, right? OH radicals also will be there. So H2 can form this, all these things it can form, right? So these are called equilibrium reactions. So for example, let's say CO2, if you want to write CO plus O, H2O you can write as H plus
Wait,
OH, right?
wait.
And similarly,
Yes.
O2 can dissociate
O
to
plus.
2O. Similarly, H2 can dissociate to 2H,
O plus.
right? So these
Yes.
are all separate equilibrium reactions you need to consider in order to calculate what are these, the coefficients of this
All products.
products, what are
Yes.
the product composition. And all these composition is assuming it will be in equilibrium, but in reality you will never reach equilibrium. Let's say in a CI engine, only for one stroke, let's say like for a millisecond, it's going to combust. Equilibrium will not be reached in a
Yes.
millisecond, right? Equilibrium can even take
Yes,
years
sir.
to reach, right?
Yes,
So
sir. Real.
so let's say if you consider equilibrium, this is still an ideal case. If you consider equilibrium, uh, you need to undergo something called equilibrium analysis, in which you can calculate all these product compositions,
Yes.
and then you want to find adiabatic flame temperature. Adiabatic flame temperature, how do you find? You will write that H of reactants equal to H of products, right?
Okay, sir.
And H of reactants is nothing but summation of R, simply if you want to write
Propane.
propane plus air, H of air.
Right.
And
Yes,
for
real.
products, So it's like mole of C3H8 and moles of air, right? Because it's a molar basis. Okay.
Yes, sir.
Similarly, for products, if you want to write, it's going to be A times C of CO2, B times H of sorry about that. CO plus B
CO,
times OH.
H2O.
All these things will come, and this is going to give
Yes, sir.
you
Yes, sir. Yes.
T adiabatic filters. So basically, you do equilibrium analysis to find A, B, C, and then you find adiabatic flame temperature. So that that detail is
Yes.
not really discussed here.
Yes, sir.
So that is what this chemical equilibrium calculation is. It is not discussed in
Yes,
detail, but
equations.
it is basically from the second law of thermodynamics. You need to include second law of thermodynamics. So what I'm trying to say is, this is first law of thermodynamics. First law,
Yes,
because Q is 0,
yes,
W is 0.
adiabatic
Adiabatic
process.
system,
Yes.
true, right? So if for an adiabatic
Yes.
system, delta H is equal to constant, or delta H is equal to 0, right? Which means H of
Zero.
reactants is
Yes,
equal to H of product. That is what
reaction.
we'll
Yes,
have to
yes,
do, right? So,
yes,
but only first law will not give you the A, B, C, D, and all. So for that, you need to
yes,
employ second law of thermodynamics, and that is what you
okay,
see
sir.
in the second law of thermodynamics. So you write entropy of product mixture, and entropy of product mixture should be, since it's an equilibrium, it should go to a maximum state, right? Entropy of universe should always increase. So that entropy of
Yes,
universe should always increase is a that you will convert it into Gibbs free energy, and you will minimize the Gibbs free energy of this system, and that is how you come up with this this relation delta G. And now you need to apply this delta G equal to 0 for this all these equilibrium reactions that we saw here.
mm,
So these reactions, we need to apply this second law to find what would be the how much amount of dissociation can CO2 happen, can H2O happen, and using that information here, you will be able to solve A, B, C, D, everything.
yes,
So it's a complex process. So that's why what people do is they use softwares.
okay,
So
sir.
basically, there are some softwares. Actually, I discussed in this class also. You can go and check some of the tutorials in which I have
Yes,
discussed
sir.
about this NASA CEA, Cantera. These things can give you the
ANSYS, on ANSYS, can we, on ANSYS, it is not possible to know about adiabatic flame temperature,
I'm
like
not able
40,
to.
40, 40.
So ANSYS has something called Chemkin.
Yes, taking to
Uh,
yes.
Chemkin tool is. I'm not really sure how to use Chemkin tool. I use open source softwares like Cantera and NASA CA. In
Acha, acha,
Chemkin,
acha.
what
Okay,
they
okay,
do,
sir.
in
Okay, sir.
Chemkin, what they do is they do most advanced calculations. Like they add kinetics also, kinetics of how
Mechanism.
mechanisms they add, right? And then they will try to come up with the pathways, how it reacts, and what are the compositions they
Yes, sir. Yes, sir.
generate, all those things. So those are more detailed calculations. So what I'm telling here is
Okay, sir. This one
preliminary
is
calculations.
simple.
Ah, so
Yes,
if you
sir.
want to get a preliminary calculation, if you want to get a simple idea of what are the things would be there,
Okay, okay, okay,
right?
sir. Okay, sir.
For that,
Hmm.
you can use these simple softwares. These are simple actually, NASA
Okay, sir.
CEA and
Okay,
Cantera.
sir.
You can
Okay,
go
sir.
and visit my other sessions in week 8 and probably week 8 or week 9, week 10 sessions will have. Uh,
Yes, sir.
I
Yes, sir.
I have discussed this in detail, so you can go and revisit that
Okay.
in order to use. These are also, useful tools. It will be helpful. It will be coming handy for your PhD also. So
Okay, sir. Thank you so much. Yes, sir.
that
Yes, sir. I will see.
you can do. So basically, that's what you use equilibrium calculations in order to get the other
Yes.
composition, product composition, and basically employ first law of thermodynamics to get adiabatic flame temperature. So that is what we
Okay.
discussed in week 8, and then you go back in week 9. We discussed chemical kinetics, about the reaction
Okay.
mechanisms and all. Uh, Basically, a chemical reaction cannot happen directly as we put it in the stoichiometric relation. First, there will be, let's say, if you
Yes,
take
sir.
a methane, first oxidizer will go and attack the, you know, hydrogen bonds. It will break, and then OH forms, and then CH2,
Yes.
CH3 will form, and then after this OH will go and break other hydrogen bonds, and it will produce a lot
Intermediate.
of
Yes,
radicals,
sir.
right? And all those things will happen.
Yes,
That
sir.
is what we discussed in the chemical kinetics. So basically, to have a
Okay, sir.
chemical kinetic, the fundamentals of chemical reaction. So let's say if you want to have a chemical reaction, uh, what is the
Yes,
rate
sir.
at which this reaction happens? So that is what is defined by this K. Where is it? So basically, you can write this global reaction like this: fuel and oxidizer gives
Yes.
products, and let's say the rate at which, how much time will it take for it to react. That is what is interesting, right? So in a CI engine,
Okay, sir.
uh, within that 1/4 of the stroke, you have to
Millisecond.
combust all the products, right, for all the reactants. So let's say the automobile is running at some speed, that stroke will be like a millisecond time. Within that millisecond time,
Yes, sir.
you need to combust all the reactants. Then only you will get
Yes.
meaningful power out of it. So for that, you need to
Yes.
know what is the rate at which this reaction happens. You cannot wait for years to reaction to happen, right? You have to make
Yes,
sure
sir.
that this reactant has to complete within this certain time. So how do we know that?
Millisecond.
So this adiabatic flame temperature or heat of combustion will not give you what is the rate at which this reaction happens. That's why we study chemical
Okay, sir.
kinetics. So here we do this kind of the rate at which fuel is, getting consumed. This is dxf by dt is nothing but
Yes.
rate at which fuel is getting consumed, and it is going to depend on
Okay,
some
sir.
some rate, right? And what is this rate is going to depend on? So we use something called Arrhenius equation to define it, and it is going to define on at what temperature it is, and also what is the activation
Yes.
energy of this reaction, and
Hmm.
there is some pre-exponential factor to it. So basically, if a reaction has to happen, what are the things required? Particle has to move, right? So all the particles, in the sense,
Hmm.
the gases has to move. The reactant
Yes.
molecules, or
Can.
and uh, you know uh, oxidizer molecule, fuel molecule has to move. So the
Yes.
temperature, the increased temperature is nothing but this motion of the molecules in the microscopic quantity, right? Temperature, what is
Yes.
temperature?
Hmm.
Temperature is nothing but the kinetic energy of these molecules inside the gases, right? So if the
Yes, sir.
temperature is high, the kinetic energy is high, so lot of collisions will happen. Lot of collision happens means reactions will happen. That is why it is going to
Yes,
depend
sir.
on
In.
temperature, right? And
Hmm.
if the EA is high, the activation energy is high, which means, let's say if I have a collision between particles, let's say fuel and
Hmm.
oxidizer
Hmm.
are colliding, right? Upon collision, what
Yes.
happens? uh, it cannot give you product, right? It needs to have
Yes, sir.
enough
Hmm.
energy in addition to collision. So that is what this activation energy is. If the activation energy is high,
Oh.
then all the collisions will not lead to reactions. Only some collision in which
Yes.
very fast fuel and oxidizer which comes and collide will react, right? So if the
Hmm.
activation energy is small, since it has negative
Hmm.
sign, exponential of
Yes.
into of small is nothing but will be large. So the
Yes.
K will be large. So if the activation energy is small, K will be large. If the temperature is large, it will have lot of collisions, so K will be large. Okay,
Yes.
so that is
Yes.
how this Arrhenius rate law is constructed. So and it
Okay.
also has a pre-exponential factor based on the size of the particle, size of the molecule, whichever is bigger, smaller. So based on that, you will get the rate of the reactor. So all this collision rate and the temperature is what is going to determine how fast your reaction is going to happen.
Yes.
So that is why we write rate law. That is the rate law. That's why we write it in terms of Arrhenius rate law.
Okay, sir.
And then we define the order and the other one, reaction order and okay, order is nothing but is m and n. You will just add it, you will know the order. So and then
Mole.
we came into reacting systems. In reacting system there are
Yes.
different reacting systems: the constant pressure reactor, constant volume reactor, well stirred
Yes.
reactor, plug flow reactor. These are reactors, different reactors in which these things can happen, the combustion can happen. So basically, in a constant pressure reactor, what you will use is,
Hmm.
why do we need to study constant pressure reactor is, you will find what is the since the constant pressure, which means pressure doesn't change, and it's also fixed mass, which means it's a piston cylinder arrangement, right? So
Yes.
basically you will get something called ignition delay. So you
Hmm.
can find something called ignition delay from this reactors, constant pressure reactor, fixed mass reactor. So let's say if you put constant pressure and temperature, initial temperature and pressure, okay, inside a reactor,
Hmm.
and if you allow it to combust, what is the time it is going to take for it to reach a higher temperature? Okay, that is what the ignition delay
Yes.
from start to end. So that ignition delay is going to
Hmm.
determine uh, it is also one of the property of the combustion system. Let's say if you have a CI engine or SI
Yes.
engine, uh, you
Hmm.
within that as I said, within that millisecond the reaction has to happen, right? And
Yes.
once you let's say spray the diesel into the engine, what it has to do is it has to after it evaporates, it will take some time for the radicals to build up, right?
Oh,
So
yes. Yes, sir.
this H and OH, so petrol also is nothing but hydrocarbon, right? So a lot of H's will
Yes,
get
sir.
generated and air will have oxygen, so it generate OH. This H, OH, O, all these are radicals, and this radical has to build up
Yes.
to a very high uh, quantity. Then only reactants flame will be set up, and then flame will go through the combustion chamber, right? So
Yes.
uh, this radical buildup will take some time, and that time is called
Yes.
ignition delay, basically. uh,
Hmm.
the
Hmm.
time it takes for it to reach a little higher temperature, let's say like a ignition temperature, how
Yes.
much time will it reach, how much time will it take for this system to reach ignition delay. And that ignition delay, we need it to be very less for a very high speed systems like a CI engine and SI
Yes,
engine.
sir. Hmm.
So
Hmm.
that
Hmm.
is where this reactor designs will be useful for us to quantify that. And well stirred reactor, you will find why do you use well stirred reactor is um,
Homogeneous mixing.
whether to, yeah, it is a homogeneous this thing. And
Charge. Yes.
right,
Yes.
it is also going to tell us what is the product compositions also at the exit. Those things you can
Yes,
get.
sir.
And uh, plug flow reactor, you will use it for to find the basically to find the flame speeds, right? um,
Okay, sir. Hmm.
so it will be the rate at which the flame moves. That is, for that also you use,
Yes, sir.
for flame speeds you will use plug flow reactor, basically. So
Okay, sir.
you have different reactor configurations which is going to quantify different properties of a combustion system. So that is why we have
Yes,
different
okay,
kind
sir.
of reactor system in order to find different properties or different
Properties
quantities
of
of a
combustion.
combustion system. And then we also discussed about multi-component diffusion. uh, it can happen,
Yes,
this is just one of the law, it can happen with different laws. And then we went into laminar flames. uh, in laminar there are two kinds of flames, one is premix flame and one is diffusion flame. Premix flame where fuel and oxidizer is mixed beforehand, and then combustion is going to happen. In diffusion flame what happens, fuel is going to come and oxidizer is going to come, and they both will meet at the
yeah.
flame, right? So they both will meet at the flame, that is what we call diffusion flame is. So diffusion flame will be something, diffusion flame is what you see in in candles,
CI
candle
engine.
flames or diffusion. CI engine also
Yes,
is
sir.
kind of diffusion flame. So in a candle what you will do, this candle is the fuel, right? And then there is
Yes,
wick,
sir.
and then there is this flame, right? So what happens is, this is the fuel, and the fuel melts in the wick, and because of capillary action the fuel comes out. And because this is at high temperature,
Yes, sir.
this is the flame will be at high temperature, not at the center. So because of heat diffusion it becomes vapor here, right? And the fuel will come here,
Yes.
and the oxidizer is available outside. Oxidizer is the air for flaming, and that will come here, and they both will meet at the flame, and they both will meet at the flame,
Yes.
oxidizer and fuel, wherever it meets it combusted, and then it generates products, and the products will go out here, right? So
Heat
that
and
is
your smoke.
as a smoke. So that is what diffusion flame is. Fuel and oxidizer is not mixed. These
Okay,
both are
sir.
different quantities. They come and meet at the flame, and then they will react. But in premix system,
Oh,
fuel and oxidizer will be mixed. So this is fuel and this is oxidizer. So these two are mixed quantity. These two are mixed quantity. Let's
yes.
say for a spark ignition engine, right? And
Spark gives design. Yes.
uh, and then you will once you ignite it, there will be flame, and this flame will, let's say, travel, okay,
Propagated. Yes.
propagate through the, yeah, through the combustion chamber. And
Whole charge. Yes.
uh, so now this, the flame which propagates, at what speed it propagates, that is what is given by the flame
Yeah.
speed.
Okay. Okay, sir.
So that is what is given by the flame speed of the combustion system, the rate at which the flame propagates. um, and
Okay.
this VU sine alpha will tell what is the shape. Let's say if you have a Bunsen burner, this is for a Bunsen burner. Let's say if you have a Bunsen burner, there will be fuel and oxidizer coming out, and there will be flame which stands on top of something like this, right? And
Okay,
how
sir.
the shape is, it will be given by this kind of relation. um, and then
Yeah.
other important parameters of this premix flame is the quenching distance, the distance uh, uh, where how much distance it takes for it to quench, this quenching distance. Flammability limits is related to equivalence ratio. What is the phi max and phi minimum it requires in order to have a flame? So all these are, during experimental condition, you need to, you cannot run with equivalence ratio of 1. Equivalence ratio of 1 means 1
Okay.
part of fuel and 10 parts of, like oxidizer.
Yeah.
With the equivalence ratio of 1, you cannot, I mean 1 means zero point 0.1, sorry, I mean zero point 0.1, right? Equivalence ratio of zero point 0.1 you cannot run, there is some limit, so phi min and phi max,
Okay, sir. That is
during which,
limited
during
limits.
within this equivalence ratio only you can have a proper flame. So that is given by the flammability
Oh,
limits, it is determined experimentally for any flame. And also
okay, sir.
ignition analysis is what the ignition delay calculation, how much time will it take for ignition, so that analysis you can do.
Yes.
And then flame stabilization, you need to stabilize the flame. You should not have a lift off or a flashback. Let's say in a Bunsen burner, or let's say in a, gas cylinder, let's say, there you do not want
Yes.
the flame to go inside the, tube, or you do not want the flame to go inside into a big place, big container where fuel and oxidizer are stored. If it goes there, then explosion might happen. So for that, you need to
Yes,
prevent the flash buffer, right? And similarly, let's say in a Bunsen burner, you want the flame to be on top of the burner. You do not want it to be above the burner. If it is above the burner, then air will go inside, fuel will become lean, and then 5 will become less
yes,
than 0, less than 1, and then because of that,
flammability
flames will
reduces.
not be there. So because of that flame, you will not able to get enough energy out of it. So these are
Temperature.
certain design quantities which you need to take care, and this is what we discussed in the lectures. And then we went into
Okay, sir.
diffusion flame, which we see in candle flames and other
मतलब डीप इंजन है सर सीआई इंजन
CI engine. Also we have diffusion flame, uh, but basically in CI engine we spray the we atomize the diesel, and
फ्यूल
we spray it inside the chamber, right? So in addition to diffusion, it forms a diffusion flame in the uh, around the droplet. Actually, it's actually will be droplet combustion, isn't it right?
यस
Shiv?
यस
Right, so it will be something like this, and then fuel will evaporate and it forms a flame outside. This is a diffusion flame.
यस
Fuel will evaporate and come here, oxidizer will be present outside, and it also going to come here, and this is where combustion is going to happen. So this is a fuel
यस
droplet, and so it's a kind of diffusion flame. This is also happens in the rocket engines, liquid rocket engines, if you
ओके सर
look at it. So there also there will be droplet and there will be combustion happening around it. And basically for a droplet combustion, there is this d square law we used to follow, which means that droplet lifetime. Let's say I have this much droplet, let's say 100 micron droplet, right? And then if
यस
I
सर
if it starts burning, right? Then what is the time it will take for it to fully get consumed, right? So let's say if the
ओके
diameter
सर
increases, the droplet time increases square of the diameter, which is why it's called
यस
d
यस
square law. So you do not want the droplet lifetime to be more, because you want to combust as soon as possible, right?
यस सर
So you will atomize your diesel droplets into a
डीजल
very small value, such that droplet lifetime will be less,
यस
let's
सर
say like a droplet lifetime of milliseconds, right? So that is what we are
यस सर
requiring. So then only it will combust, and you will get enough energy out of it, right, within that stroke. So that is
यस
why
सर
use something called d square law to find it. And then we have droplet burning rate constant, and this burning rate constant, it has a equation which is going to depend on temperature and other quantities.
यस सर
And then we discuss something about pollution also. uh, we need to follow pollution emission, you know
यस सर यस
limits.
सर
That is one of the research actually going on with automobile engines, right? We need to
यस यस
reduce the
सर
emission as less as possible, carbon emission. So that was the
यस
last
यस
topic we discussed in this.
यस यस
All right, I hope this revision would be helpful for you. Do you have any
यस सर
additional questions, Shiv?
नो सर नो सर
All right.
very helpful sir sir thank you so much sir
Thank you, Shiv. I'm
I
glad to
I,
be
I
able to.
got along with basic concept of thermodynamics and combustion. Simple things I don't know, but you clear my doubts. Thank you so much.
So what you could do is you can read
Yes,
Stephen Turns. Okay,
yes, sir,
it
yes, sir.
will explain
Sir,
you.
can I got that PDF or any soft copy? Either I have to buy that book.
Which one?
Stephen
R turns, is it?
books.
So
Yes, yes,
I'm not sure whether you can get it in PDF, but I think you can visit library and there they should have Stephen R turns.
yes, sir. Maybe
Yeah.
also.
Either you can visit library, or if they don't have, you can ask them to buy a Stephen R turns. Or your
Yes, sir. Yes.
supervisor might also have Stephen R turns, so you can ask for him also.
Okay, sir.
Uh, so
Okay,
that
sir.
book,
Okay, sir.
so Stephen R. Turns is a good book. You can learn a good, good amount of concepts, basic concepts about combustion.
Yes, sir. Yes, sir.
It would
Yes,
be
yes,
helpful.
sir.
And also you can. So do you know about this? So there is this problem solving session, right? So there is recordings
Yes, sir.
also I've shared. You can visit that also
Yes, sir.
if you.
Okay, sir.
So there also I have revised certain things like week 8, week 9, week 10, week 11, week 12. These
Okay, sir.
things you can visit and you can. Basically, I discuss something related to NASA CEA and Cantara, how you use it. So those things you
Okay,
can.
sir.
It
Okay,
would
sir.
be
I will.
helpful for you.
Yes.
Uh, so you can
Yes, yes,
visit
yes.
that also. It is available in the
Okay, sir.
in the same forum. Okay.
Yes, yes.
All
Okay, sir.
right.
I will
Sure.
leave, sir.
Sure.
Thank you. Thank you so much, sir. Thank you so
Thank
much.
you, Shiv. Thanks for attending. All right. So
Okay, sir. Thank you.
if there are no questions, I will close this session. Again, if you have any
Okay,
doubts, you
sir.
can put it in the common forum. I will try to answer it
Yes.
if possible. All right.
Okay, sir.
Right.
Thank you so much.
Thank you, Shiv. Thanks for attending. Bye.
Thank you, sir.